In this next step, we'll be making decisions about recording data in ways that will help us answer our questions. This process is also known as data management.
Data management involves making decisions about data. The codebook and frequency distributions are an excellent guide for making these decisions. In fact, many decisions that you make will be based on examining frequency distributions. You will use them often because they reveal things about the data that will be helpful to you.
There are several steps commonly considered when conducting your data management. You may only need to perform a subset of these steps. It is even possible that your variables are already adequately managed and no data management is necessary. In all cases, it is important that you consider each possible decision because it allows you to play an active role in understanding your data and assuring that you are asking your questions in an appropriate and meaningful way.
A first step to consider is whether or not you need to code out missing data. We'll use our young adult smoking project as an example. In the NESARC codebook, you see that the response category 1 means daily smoking for variable S3A Q3B1. And you can read down to see the meaning of other response categories for the usual smoking frequency variable and frequency table. Your data will often include response categories that don't help you answer your question, even though they provide information. For instance, in this variable, we have a response category unknown, coded as a 9. For these responses, we simply don't know how much these individuals smoked, and therefore we don't want to include them in our analysis. We want to set this response to missing to ensure that SAS disregards these values. The logic statement that we add to our program to accomplish this is if S3A Q3B1 equals 9, then S3A Q3B1 equals period or dot. This followed by a semicolon. We're telling SAS that any observation on this variable should be recorded as a period or dot. A dot is the way that missing data is specified in SAS. Here's another look at the SAS program we've been building for this example project. As a reminder, it's important that all of the syntax you write to actually manage your data is placed in the data step of your program, after the data statement, but before the proc sort statement. If you have any logic statements that subset your data to specific observations, your data management syntax should precede these logic statements, which directly precede your proc statements. To check that this logic statement accomplishes what we intended, we're going to comment out the variables in the table statement for all but the smoking frequency variable S3A Q3B1. Given that the syntax that we included in the comment is listed in green font, now none but the smoking frequency variable will be read by SAS when the program is run. So at this point, we're going to save and run the program and replace the results from the previous run. As you can see from this new frequency table, the 3 cases that were set to 9 are now included in the missing group as we intended. So this variable has been managed. Let's consider another of the variables in the sample project, S3A Q3C1, the variable usual smoking quantity. Here's the codebook entry for this variable. Usual number of cigarettes is indicated by values of 1 to 98. A value of 99 indicates an unknown response. It's this value that we need to set to missing, since it doesn't measure the number of cigarettes smoked, but rather indicates that we have no information on cigarette use for individuals who are coded as a 99. The logic statement we need to add to this program to set 99 as missing is if S3A Q3C1 equals 99, then S3A Q3C1 equals dot, semicolon. We add this logic statement within the data step, add this variable back into the table statement, and then save and run the program. As always, check the log to see if there are any error messages, and then view the results. When we scroll down to examine the new frequency table for usual smoking quantity, we can see that the 9 observations that were originally set at 99 are now in the missing group. So what's next in data management? When we examine the frequency distribution and the codebook entry for the tobacco dependence variable for our sample project, we see that this variable has only valid responses. That is, 1 equals nicotine dependence, and 0 equals no nicotine dependence. So this variable will not require any data management for missing this, and we're set to move forward.
Please note that it is important that you examine each of the variables that you've selected and add syntax to your program that recodes appropriate data as missing. Once you have completed this portion of the data management, the next step is deciding whether or not you need to code in valid data that has been unnecessarily set to missing.
Well, in some data sets, particularly those based on surveys, there are often skip patterns. So you may ask participants in a survey, have you ever been arrested? And a respondent may say no. If the next question in the survey is how many times have you been arrested, for a participant who already reported never having been arrested, this second question just doesn't make sense. To avoid asking inappropriate questions, skip patterns are often created in surveys that allow participants to skip questions in which the answer can be logically determined. In this way, missing data on some questions might mean that we can reasonably recover valid information.
For the question, did you drink at least one alcoholic drink in the past 12 months, 16,116 participants said no. These individuals would not need to be asked the question about how often they drank alcohol in the past 12 months. Instead, they would be set to blank, or in the case of a SAS dataset, a dot or period. So for the variable, how often did you drink alcohol in the past 12 months, it would be reasonable to code this as valid data rather than missing.
To recover this valid information, in our program, we would use the logic statement, if S2A Q8A equal dot, then S2A Q8A equal 11 semicolon. In other words, if how often drank any alcohol in last 12 months is blank, that is shown as a period or dot in a SAS dataset, then we know that the individual drank 0 times in the last month and we can give them a valid code. We also need to add if S2A Q3 NE9 to our logic statement in order to separate the 16,116 no responses to the question of did you drink at least one alcoholic drink in the past year from the 31 observations whose answer was unknown, coded as a 9. So the complete logic statement is, if S2A Q3 NE9 and S2A Q8A equals dot, then S2A Q8A equals 11 semicolon. So here, rather than left as missing, we're adding a category to this variable with the dummy code of 11 to indicate those participants who did not drink alcohol in the past 12 months.
Another very useful step in data management is to give your variables response codes that may be more logical than those they were originally given. For my variable, usual smoking frequency, you can see from the codebook entry that lower values mean that the respondents smoked more, and higher values means the respondents smoked less. Perhaps this seems counterintuitive to you.
We could choose to reverse code this variable so that higher values mean more smoking and lower values mean less smoking by adding the following logic statements. This is syntax that creates a new variable called USFreq, USFREQ. that reverse codes each of the smoking levels. Now, smoking every day is a 6, and smoking once a month or less is a 1, and all intervening levels have been appropriately reversed also. Rather than using the original variable S3A Q3B1 in our analysis, we will use this new variable US_freq. However, it's important to add these details to the codebook and to the program so there's good documentation of this decision as we move forward. But there's actually another option that may be even better for giving this variable codes that are maximally appropriate. In a way, dummy codes 1 through 6 are unnecessarily categorical, given that how often you smoke is generally a quantitative variable, and it may be reasonable to recode the variable in order to capture more of its quantitative features. To do this, we choose values that reasonably correspond to the number of times each individual smokes in a usual month. So someone who reports smoking every day could be said to smoke cigarettes on 30 days in a usual month. Someone who smokes 5 to 6 days a week could be said to smoke 22 days in a usual month. Someone who smokes 3 to 4 days a week could be said to smoke 14 days in a usual month. Those smoking 1 to 2 days a week would be 5 days in a usual month. 2 to 3 days a month would be 2.5 days in a usual month. And once a month or less would be 1. Although these are estimates, they capture the quantitative nature of the measure and also keep individuals ordered in terms of the frequency with which they smoke. Note that the way we've written the syntax, our new variable is called US_freq_MO, which stands for number of days smoked in a usual month. So this even makes more sense, doesn't it? What we've basically done is to spread the measurement of smoking frequency out in a meaningful way, so that while it's a categorical variable, we're actually getting more information out of it than we had originally been given. And when we add this syntax to the program and request a frequency table, the table now describes the sample of 1,706 young adult past-year smokers somewhat more clearly by showing the numbers and percentages of individuals who smoke these approximate number of days in a usual month. You can see that the vast majority of the sample, 1,320 individuals, or 77.51%, smoked 30 days a month. Fewer than 5% smoked 1 or fewer cigarettes a month. One of the later steps in data management is evaluating whether you might want to create secondary variables. Secondary variables are variables that include information from 2 or more primary variables. We can create secondary variables by using a mathematical or logical operation on 2 or more variables. In this case, we want to know the number of cigarettes smoked per month. We know the number of days smoked each month, and our new variable, US_freq_MO, gives us an estimate of the quantity smoked. If we want to estimate the total number of cigarettes that participants smoked per month, it would make sense to multiply these two variables and get a product that represents the number of cigarettes per day times the number of days smoked per month. Let's call this new variable numSig_MO_EST, which stands for the estimate of the number of cigarettes smoked per month. So the syntax would be numSig_MO_EST equal to US_freq_MO asterisk S3A Q3C1 semicolon. If we add this line of code to the program and ask SAS to show us the frequency distribution for this new variable, numSig_MO_EST, is a quantitative variable that ranges from 1 to 2,940 with 9 missing observations. So how can we check to make sure that this new secondary variable was created as we intended? For this, we're going to learn a new SAS procedure. The procedure, or proc, is called print, and it allows us to view data for each observation individually, according to whichever variables we'd like to see. So, after the data step and after the proc sort statement, in the section of the program where we ask SAS for specific results or output, we're going to add the following syntax: proc print semicolon var, indicating variable, followed by a list of variables that you would like to examine for each observation or individual. Since we want to see if the new variable, number of cigarettes smoked per month, is indeed the product of multiplying frequency per month and number of cigarettes per day, we include the following variables: US Freak MO, S3A Q3C1, and the new secondary variable numsig MO underscore EST. As always, end the statement with a semicolon, and after saving and running the program, first check the log for errors and then view the results. For the print procedure, the output looks a bit different. The rows represent individual observations similar to the data set itself, and the columns show the values for the specific variables. Looking over these values for a handful of individuals, we can see that, in fact, our new secondary variable does indeed show the value of number of days smoked per month times number of cigarettes smoked per day. Remember that whenever you're conducting data management, it's important to find a way to check for errors at each step of the process.
So what if you want to combine more than two variables? A good example of this would be creating a single secondary variable to characterize ethnicity from a number of separate primary variables available in the Add Health data.
In Add Health, race or ethnicity are measured by a series of questions, coded 1 if yes and 0 if no. Since adolescents in this sample could have indicated more than one race or ethnicity, we could decide to characterize those adolescents who indicate multiple racial or ethnic groups separately from those who could be characterized with a single ethnicity. To accomplish this, the first thing to do is sum the variables to get a new variable, which we'll call numEthnic. That indicates the number of race or ethnicity variables that were endorsed. The syntax would include the new variable's name equal to sum, open parens, of, and then each of the variables listed with only a space between them, followed by a closed parens and a semicolon. Next, we add logic statements that create a single secondary variable that characterizes each adolescent's ethnicity. So, if numEthnic is greater than or equal to 2, then the final ethnicity variable, which is called ethnicity, is equal to 1, indicating multiple racial or ethnic groups endorsed. Else, if H1GI4 equals 1, then ethnicity equals 2, which means only Hispanic or Latino ethnicity was endorsed. Else, if H1GI6B equals 1, then ethnicity equals 3. Only Black or African American ethnicity was endorsed. Else, if H1GI6C equals 1, then ethnicity equals 4. Only American Indian or Native American. Else, if H1GI6D equals 1, then ethnicity equals 5. Asian or Pacific Islander only. Else, if H1GI6A equals 1, then ethnicity equals 6, for white ethnicity only. When we add the syntax for data management of ethnicity, request a print as well as frequency tables for the primary and secondary ethnicity variables, and save and run the program, here's what we get. We have our print output, which shows the values of the primary and secondary ethnicity variables for each observation, in this case, each adolescent. At the end of the results, we have frequency tables for each of these variables. This program is available as text below this screen. We suggest you copy this text and paste it into a SAS program window and select Run. Examine the output and consider how this kind of data management might be useful in answering your question with your data set. This example should help you make the needed connections between data management decisions and syntax. Once you've created the secondary variables that you feel you will need, you can also consider whether any of your quantitative variables or categorical variables need to be further grouped or binned. As an example, we're going to show you how we might choose to group age in the NESARC sample. If, rather than looking at age as a quantitative variable, we may want to compare age groups categorically. We could examine the number of observations at each age and make some decisions about how we could best make groups. Here's the frequency table for age in our young adult past year smoking sample. The cumulative percent column displays percentiles that can help you divide the sample into a specific number of equal parts. If we wanted 4 age groups, we would look for cumulative percentages that are closest to 25%, 50%, and 75%. If we wanted 3 age groups, we would look for cumulative percentages that are closest to 33% of the sample and 66% of the sample. This is the syntax that would create a categorical variable that divides the sample into roughly 3 equal size age groups. We chose the age cut points of 20 and 22 because these correspond roughly to the 33rd and 66th percentiles. The frequency distribution table for our new variable age group shows the 3 age groups and the percentage of observations in each group.
Now that you've seen a number of different data management decisions that could be made, I hope that you're ready to take on your own, which you will do in the next assignment. How much data management you will need for your own variables will depend on the variables that you've selected and the decisions you've made about them. Some may choose to only code out missing data, while others may need to or want to do more. Data management is a part of the research process that you can and will return to again and again as you learn more and are able to make better decisions.